Okay, so let's just wait until the number of participants gets stable.
Mm-hmm.
And then we start.
Okay. So you said you're handing it over the seminar to other organizer from this end of year, or no, maybe.
Sorry, I didn't hear you. Sorry, I was doing something here.
I think Ivan was saying that you're handing the seminar over to other organizers.
Oh,
right.
yes, yes.
Actually, they're both on. So Amanda Turner, who will, I think, chair the second talk, and then Alessandra Fagiotto.
Okay, so let's go ahead. Welcome everyone to actually the last meeting of this year of the One World Probability Seminar. So as usual, these seminars are being also broadcast on the YouTube channel of the seminar. In case you have a unstable connection, you can catch up there if you have any trouble with your internet. And so it's a pleasure to introduce Thierry Bodineau, which is going to give the first part of this two-part talk about the spectral gap and log-solid inequalities for strongly correlated spin model.
Well, thank you very much for this invitation. It's a great pleasure to talk on this occasion, and I'm going to report on the joint work with Roland Bauerschmidt, and we're on a series actually of work, and he's going to present the second part afterwards. So the first part will be trying to recall some general facts on the relaxation of lattice model dynamics, explain a bit what are these functional inequalities for those who are not familiar with spectral gap and log Sobolev, and then explain why or how we use this the renormalization group and the Polchinski equation in order to derive some kind of multi-scale Bakry-Emery criterion. So that's the aim of the talk. And the second part, Roland will show how from this strategy one can get quantitative results and explain this in case of a few concrete examples, namely hierarchical models, so continuum Sine-Gordon model, and SK model. So let's start with a kind of a prototype of a model we are interested in. Basically, in this talk, what we want to look at is oops, sorry, not quite yet. It's dynamics which have a continuous spin system. And we are interested in, let's say, the analog of Ising model. Basically, the spin or each spin lives in a potential V0, a double well potential, like here. And they have a quadratic type of interaction. There's a quadratic type of interaction between the spins, where one spin, say over here, is going to interact with its four neighbors. So that the model, and with this model we can build a Gibbs measure over there. I mean, standard definition of the Gibbs measure, which depends on the Hamiltonian and what in general one expects. Even so, I will not go into the detail, but is a phase transition with some critical value, and depending on the parameter t over there, there'll be either a phase transition or no phase transition when the volume of the dynamics goes to infinity. So that's the type of model we have in mind. At the same time, of course, what would be interesting is to understand the dynamics. So what I will call continuous Glauber dynamics, and it's just this Langevin type of dynamics for each spin xi. Feels the derivative of its potential and some independent noise at each side. So tuned in this way, the Gibbs measure defined in the previous slide is the invariant measure. And what we are interested in is to show how fast the measure at time t, the due to the dynamics or from the dynamics, is converging to its limiting measure nu. So when one has a dynamics of this form, basically it boils down, or to understand the measure mu t, we introduce the semigroup associated with these dynamics and let it evolve under the we introduce the generator and let it evolve under the semigroup. So basically, if initially the measure doesn't start from nu lambda, but from a measure mu zero far from nu lambda, then it's going to evolve at each time according to the equation which is here. So the question we are interested in now is, can we quantify this speed of convergence, and can we say something how fast mu t goes to the invariant measure? We can, I mean, this can be reformulated as follow in terms of the function ft, because since nu is just mu t is given by ft times the invariant measure, we just want to know how fast ft is converging to 1. And there are several ways to quantify this. I mean, standard one is to measure the variance somehow between mu t and nu, or basically the variance of the function ft. And if, so this is a notion of distance between ft and 1. So we want that ft converges to 1. And we know that Poincaré, or we will say that a Poincaré inequality holds with a spectral gap given. Yep.
I think we are missing a little bit of your slide in the
at the top. Yep, it's not working as well as I wished. Wait, you mean this one? Doesn't really want to disappear. Okay, disappears sometimes and comes back. Sorry about that.
That's okay.
I'll try to make sure it's it's on. So the spectral gap lambda is going to help quantifying the relaxation of the variance of mu t with respect to nu. And one thing I'm going to use heavily is this notation gradient of f square, which is just the sum of the square of each gradient. And the Poincaré inequality basically has to hold for any function f smooth enough in order to take the derivative. And if this is if there is a constant lambda which holds for any function f, then what one can deduce is the last line, namely that the variance is going to 0 exponentially fast. So that's a consequence of the spectral gap. And in the same way, one can also measure another distance, namely the entropy, which is defined there. So maybe I'm going to move it. Oops, sorry. So here, the entropy is defined in terms of the function u log u, and we'll say that a log-Sobolev inequality holds if this is satisfied for any smooth function. So essentially, it has the same form as the spectral gap inequality. It's a bit different now because phi is no longer a square, but u log u. And as a consequence of a log-Sobolev inequality, if this holds for a constant gamma positive, then one gets now a decay of the entropy, exponential decay of the entropy. So that's the kind of statement we want to understand in order to get quantitative convergence of, say, the entropy or the variance when time goes to infinity, which ensure a quantitative convergence of the measure mu t to its invariant measure, or to the invariant measure. Okay.
Thierry?
Yep.
Just a quick question, maybe it's a little bit silly, but you are talking about the Poincare inequality, which is something that holds for any function f.
Yes.
And then you use it only for this function ft.
Yes, indeed. The point is that what we don't. Yes, we use it only for ft, but a priori we don't know really how ft is. So I agree that it's a bit too demanding because we kind of control all the function and we use it only for one. But a priori, this ft can take a very general form, and that's why we okay. It's just a consequence. After, as you know, once one has a good log-Sobolev or a good Poincare inequality, one can do many other things. But at least that's one of the justification is to get quantitative convergence.
But is there a sort of notion that you could get a priori estimates from your PDE structure that would allow you to get stronger results without this level of demand?
Sorry, I didn't get your question. You mean?
So in improving this type of convergence result, would a priori estimates not help you?
Not that I know. I have to confess. No, I don't.
Taking advantage of the structure of the PDE.
Certainly, at some point, we're going to rely very much. I mean, at this stage, it's still relatively general. And at some point, it will depend very much on the structure of the PDE and of the dynamics we're going to look at. And in any case, to get quantitative estimates, and I'll say later on what we mean by quantitative, it will depend very much on the structure of the equations we are looking at. One cannot, I mean, there's no hope in general to get general estimates, or at least it's rare.
Thank you.
Okay, so let me just to give an idea of how one goes from a spectral gap, a log-Sobolev inequality, which is in gray here, to the convergence of the entropy, because it's something which will be useful later on in the proof. So just to get familiar with this type of strategy. So basically now we want to prove the exponential decay. So let me recall you that the function ft from which the measure mu t is defined at time t is given in terms of the semigroup, the evolution of the function f0 along the semigroup. So the strategy is the following. Let's start taking the derivative of the entropy, and this boils down to take the derivative of pt f0, which is related to the semigroup generator. So when one does that, it may look ugly the first time, but it turns out that doing some integration by part, one can easily reformulate the derivative of the entropy in terms of something relatively simple, which is the Dirichlet form associated with square root of PTF0. And at this stage, the log Sobolev inequality will help in order to close the equation, because if one, if one plugs in if one plugs in the log Sobolev inequality, one can close the equation in terms again of the entropy and gets the exponential decay. So the idea is we have a semigroup, we take the derivative with respect to the semigroup, and there are nice structures which are appearing. So we're going to keep that in mind. So let me now be a little bit more specific in terms of the decay. What will be relevant for us are these parameters, gamma lambda, which is the log Sobolev constant, or lambda, which is a spectral gap, and they both depend on two parameters. If you think of on the first model, the domain and the temperature. And of course, if we know at least that at equilibrium, when the domain goes to infinity, there is a phase transition, and we expect that this will have also consequences on the relaxation of the system. So I just wrote a series of names of many people who have been thinking about this problem, and for the, let's say the log Sobolev constant. It is only known for high temperature that the constant is strictly positive uniformly with respect to the size of the system. And there is not a very quantitative result in this case. So let me mention Ising model, because now we will not be working exactly on that, but I think people are more familiar with it, and it's useful to make some comparison with what is known. So for Ising model, essentially the same. It's a discrete version. So now it's not a double well. The spin take values +1 or -1, and there is some Hamiltonian which forces the spin to align. The Gibbs measure is defined here, and again there's a phase transition. So here I'm afraid for Ising it's kind of natural to write the beta as the inverse of temperature. So all the phase diagram is inverse of what I wrote before. And the dynamics now is the Glauber dynamics. So basically one chooses randomly one point or one site and update it in terms of its four neighbor, such that the dynamics remains, or the Markov chains remains reversible with respect to the Gibbs measure. And we can ask the same question as before, namely, can we say something on gamma and lambda? So for Ising model, situation is actually much better. And the uniqueness of the Gibbs measure is known in very strong sense, leading to quantitative result, at least for the spectral gap, up to the critical temperature in dimension 2. And actually, even in recent work by Crawford and De Ruck, this quantitative decay to equilibrium has been improved in any dimension. Now the point, of course, which we will be interested later on is what's going on when we get close to the critical temperature. So there are very few results in this regime, and I just want to mention the result by Lubetsky and Sly in dimension 2, where they showed that right at the critical temperature, beta critical, they were able to prove a lower bound on the spectral gap. And the lower bound now decays with the size of the system. It's certainly one expect a decay, even so this parameter gamma is not the correct one, and the actual critical exponent is for gamma, or is not known there. And the kind of issue we will be interested in the continuous context is trying to say some quantitative result in this region when beta approaches to beta critical, or in regime where the system is close to criticality. So far in Ising model there is not many results to my knowledge, at least.
I have a question.
Yes.
Could you clarify the situation in 1 dimension and in 3 dimensions? What's known?
Oh, in 1 dimension, I think it's pretty. I mean, it depends. If we're talking about Ising model. So for Ising model,
the Ising model. Just discussing especially the exponent.
Oh, there's no exponent in 1. Sorry, so in 1 dimension there's no.
One and 3 dimensions.
Okay, so in 1 dimension there's no critical parameter. I mean, there's no phase transition. So there, everything is fairly well known, and at least it's strictly put. I mean, the exponential decay up to how's it called? There's exponential decay for any beta. In 3 dimension, what is known is that not at least I think in dimension 2, when very strong results are known uniformly with respect to the boundary condition. So I think in 3 dimension the results are only known in infinite volume and not for every boundary condition. But essentially, it gives a decay, including as well when there is a magnetic field. For the spectral gap, the situation, for Loxo-Bolev, the situation is not clear, as clear at least. I don't think it's known up to the critical point.
Yeah, I was just trying to clarify that in 2 dimensions you have sort of exotic behavior you have conformal symmetry, I thought, at the critical point. Conformal field theory at 2 dimensions is quite different than in higher dimensions.
Okay, so everything, sorry, you're right. So everything I was saying, what is actually understood and under control in any case is mainly for beta less than beta critical, strictly less than beta critical. And this is only a bound. And I mean, there is, to my knowledge, there's nothing in 3 dimension.
Yeah, thank you.
Okay, I will come back actually for the reason why there is nothing in 3 dimension. And the point is that all this approach rely on the following ideas. Is when you look at the independent variable, let's say the case of Ising model, when beta is equal to 0, then the spectral gap do not depend on the domain. So spectral gap, Loxo-Bolev inequality, they tensorize, and you can take as many variables as you want. You get the same bound, the one which correspond to the you get the bound which is for which is for a single spin. So like here. Now the idea is to say, okay, in the uniqueness regime, when beta is less than beta critical, the system should be weakly dependent. So even so, there's some correlation. If I look at two blocks far apart, they're going to interact very weakly, and I shouldn't be too far from the independent case. And the whole idea, which have been implemented, is to perform a kind of spatial renormalization with block decomposition. And if one has a very good understanding of the equilibrium measure and refine decay estimates, then one can deduce also good estimates on the dynamics. So that's the strategy. Renormalized, the system and look at big blocks and hope that these blocks become relatively independent due to good estimates on equilibrium measure. And from that, one deduces decays or good estimates on spectral gap or log Sobolev. So now what we would like to understand is, can we say something? We know that when beta goes to the critical temperature, the correlation are increasing in the system. We know that the Glauber dynamics should slow down. And of course, the issue would be, can we say something on the spectral gap and log Sobolev in this region, and in particular, if one has beta which is approaching beta critical, can we get some scaling exponent or dynamical critical exponents with respect to this distance? So I will not go into the details, and Roland will make it much clearer later on specific models. A priori, for Ising model, this question, as it is posed, is delicate. It depends also on finite size scaling, maybe boundary conditions, and so on. But clearly, what we would like to understand is when the system gets close to criticality, whether something can be said about the dynamical exponents. So that's the aim or the goal of this talk. Of course, over there, I mentioned also, sorry, something. What would be interesting is when one is exactly at beta critical, or namely, if one uses some finite size scaling, can we get the polynomial exponent depending on the size of the right polynomial decay depending on the size of the system. So all that is for Ising model is not known at the moment. And actually for the model I started with, the 5.4 is not known either in such a generality. Okay, so let me just summarize now this comparison. What we are interested in this talk is discuss unbounded spin models. And the approach which have been implemented so far were very much in the spirit of the block decomposition I mentioned earlier, with the extra difficulty that in unbounded case, getting uniform bounds on the correlation is difficult, and therefore there only a little part of the phase diagram is under control, namely when the temperature is high enough. Let me mention that this idea of block decomposition also in the unbounded spin model has been heavily used as well for conservative dynamics and by Mentz, Otto, and Wand and Mentz as well. Okay, so let's come back to something which looks or which might be a little bit different, but there's a very nice property for continuous model which is due to Bakri-Emery and which ensure that when the potential or when the Hamiltonian has a nice the Hamiltonian H here as a nice convex structure, then the system relaxes fast. So basically, the theorem is the following. So imagine now that the Hamiltonian, sorry, which is here. Oops. Okay, maybe I'll stop here. The Hamiltonian, which is here, is decomposed into two parts. The first one is a quadratic part, and we add a potential V. then if the quadratic part is bounded from below by some gamma times identity, gamma positive, if the other part V is non-negative, sorry, the Hessian of V is non-negative, then what has been shown by Bakri-Emery is that a log-Sobolev inequality holds in this case with a parameter gamma given by the lower bound on A. So it's somehow natural that in a convex or strictly convex environment, there's a fast relaxation. It's like having a ball dropping into a well, and it goes back fast to equilibrium. This is a nice feature, and I would like to recall it. It's specific in a sense to discrete to continuous dynamics. Even so, it has been or there has been or there are many works trying to extend it to the discrete setting. But in the continuous case, it's very neat, and I would like to show you the proof. So what we want to prove is the inequality above, which is the log Sobolev inequality. So let me recall you that phi is u log u, and the strategy which has been devised by Bakri-Emery is to prove this inequality by using the dynamics, by using the semigroup of the Glauber dynamics I presented before. So this semigroup PT as this generator of the dynamics, and what of course in the what we would like to what we want to prove is that this term over there is less than the Dirichlet form. So the strategy is to look at this term and interpret it as a difference between the function f taken at initial time under the semigroup and the function f taken at time infinity, namely when the semigroup runs to infinity, we just get the invariant measure. So this way of writing the difference means that we can proceed exactly in the same way as I proved the relaxation of entropy at the beginning of the talk. We just take the derivative between time 0 and infinity and say that this difference is just the integral between time 0 and infinity of the derivative. The derivative, we computed it earlier in the relaxation of the entropy, and we get some expression. There, it's much more delicate because now we would like to close the equation and recover the log Sobolev inequality. So at this stage, one needs the assumption of convexity, and this assumption provides an inequality which allows to replace the gradient of the square root of the semigroup by something which no longer depends on the semigroup, and we get some decay. So that relies on a delicate computation by Bakri-Emery, and definitely to get this gamma, this parameter gamma, requires to know the strict convexity of the potential. But once one can use this, or once one knows this inequality, then the proof follows, because this term can then be replaced by this one, and it's enough to integrate the last part in time, and in order to recover the log Sobolev inequality, which is here. Okay, so the idea was, I insist because I'll come back to that again. Let's take the semigroup of the Glauber dynamics, let it act on the entropy and see how things evolve, and from that obtain a nice inequality due to the convexity. Okay, so the main drawback with this approach is that the first model we looked at is not convex at all, because the spin live in a potential, a double wave potential V0, and okay, this approach simply doesn't work usually for spin systems. So it's beautiful because it relies very little on the specific structure of the model, but it requires strict convexity. So next,
I have a question.
yes.
So in the double well potential, the depth of the well, that's connected to your parameter beta, yeah?
Yes, actually here over there, but it's okay. That was to simplify. The beta is related to the parameter t. So when t goes to 0, beta goes to infinity, and it's going to fix the spin at the bottom of the. I mean, the spin prefer to stay at the bottom of the potential, but it's not the okay. It's probably not the best. You may. I mean, Roland will explain in his talk that you want actually to tune as well. In order to see things, to add some parameter in the potential and to tune them as well.
Yeah, it was just to somehow raise the point that as you reach the critical point, as the well becomes essentially almost convex, at the minima, its Hessian is 0, but its fourth derivative is positive. That's the criticality point, yeah?
Not for, okay, that would be in a kind of mean field model, but what's happened is that so let's say the V0 is somehow fixed, and with a double well for every spin, then you have a competition between all the spins and their interaction, which, if you look at a Curie-Weiss model, looks like, let's say, the free energy becomes like X4 at criticality, but it's more complicated
Thank you.
in the discrete lattice case.
Thank you.
And another another model Roland will discuss, and it's another example, relatively natural, of non-convex model, is a Sine-Gordon. Sorry, it's a Sine-Gordon model, and the Sine-Gordon model is okay. Are there questions, or it's okay? Okay. The Sine-Gordon model has a quadratic interaction. Oops, not this one. Sorry. The Sine-Gordon model has a quadratic interaction and another potential which now depends on the cosine, so it's not convex at all. There's a small addition of some convex part here, but it's tiny, so so in a sense one shouldn't think of it too much for the moment. So in this case again, one has a kind of quadratic form, the first part, and one has a perturbation, z small, but not 0, which is non-convex. So again, in this model, the Bakry-Emery criterion cannot be applied directly. So just to fix ideas, let's see what's going on and what are the important features in this model. So we start with a periodic domain. So in a periodic domain, of course, one needs to add a little mass, otherwise the field, epsilon square, otherwise the field would wander to infinity. But this type of potential, we're going to decompose it into two parts. One part is the quadratic form, A, and the second part, the nonlinear, we call it V. Then in this case, the matrix, or A, is bounded from below by the tiny Gaussian epsilon square we added, Instead, the nonlinear part v of the Hessian v of x is bounded from below by minus z times identity. And there we see that the potential is not convex as soon as z is larger than epsilon squared. However, what is interesting in this picture is that the convexity or the non-convexity arises because there are different features in the model. There's on the one hand, the A comes from a Gaussian field, and it has long-range correlations, but very weak overall straight convexity. And the other part, the local perturbation is short range, and this one is not convex at all. And if one try to think of it slightly differently and decide, as in the picture below, to freeze all the spin around around the spin here in the center, and we just look at a single spin, then the potential felt by a single spin is actually much more regular than one thinks, in a sense that it's becoming convex, because if all the neighbors there are frozen, this guy is going to feel a quadratic potential which is quite strong, and the perturbation by the cosine will be relatively small in comparison. So the idea is that for this type of model close to criticality, or which are at criticality in this case, the specific structure can be helpful in order to prove relaxation, and we need to implement this or to look at it closely. Let me to give you an idea. I just want to make a very brief overview of the renormalization group strategy at equilibrium, and explain the general philosophy. So if we start from this type of Hamiltonian, so the Sine-Gordon model, and we look at a system in a domain I, so each spin is indexed by the site I, and these are the blue dots. Now these blue dots will be the level 0, and we want to renormalize and make some blocks, and the idea is that once the system, if we can look at larger blocks, let's say the black ones, which are containing the value of 4 spin, and maybe average the system in a certain sense on each of these blocks, well, we expect that we should have a model with a structure relatively similar to the original one, except that the field x1, once renormalized at the level of the black box, will have a similar interaction, but with a z which is lower than the original z. So once you average over blocks, you expect that your system gets more regular and gains in convexity.
So quick question. There's something missing from the bottom of the slide. I'm not sure if you're annotating that. We're not necessarily seeing it.
Sorry, I do have some issues with my iPad. Sorry. Okay, I don't think. Yeah,
the thing I'm interested in understanding is why Z should be smaller for the renormalized blocks. What's the intuition why Z should be smaller?
Okay, so in this case, what you expect is that the first Z is adding a very short, perturbation, local perturbation, and once you start averaging it out, this will disappear, at least partly if you do some averaging at a certain level. And
So
therefore,
is this some sort of Jensen type argument with convexity?
oh no, it's. I mean, you need to integrate the whole thing and check it out. No, it's much deeper. Actually, what I'm saying is very heuristic, because when you integrate or when you average on blocks of size like the black boxes, you don't get the same Hamiltonian. You get something much more complicated. But in principle, even so, it's more complicated. It should behave better.
So that renormalized Hamiltonian, that's the so-called RG flow. You're basically evolving in parameter space, yeah?
Yes, except yes, it's just and if you average on higher level, let's say the red one, now you move to Z2 and a better parameter and so on and so forth. So you hope that essentially after proper renormalization, your system will be under control. So that's the general philosophy, and it's delicate, very delicate to put into place, and has to be done for every type of model. It's not that general, and actually Roland will be much more precise on the scaling, and will give further references. But what I want to say is that, as I explained before, there was a notion of renormalization to show that the spectral gap remained, or the log-Sobolev constant remained positive, but the idea was more like the blocks are decoupling. In the kind of model we are looking at, we're not going to hope even that the block decouple, because the block will be still interacting very strongly, and for example, the limiting structure will still be a Gaussian free field, for example. But the idea is that the block still should have a better structure, and once averaged, there should be a kind of field which should help us to solve the problem. So now the question we're going to try to answer at this partly is, can we do something or use the renormalization group which has been developed at equilibrium to analyze dynamical features such as the log-Sobolev inequality? And for that, I will explain to you this multi-scale Bite-Emery criterion we obtained with Roland, and it heavily relies on Polchinski equation, which in particular was studied in a paper by Bridges and Kennedy, which was a great source of inspiration for our work. So let me now explain how we're going to use this very formal renormalization group idea in our context. So we start with a general Hamiltonian, which is here. Again, some quadratic part, Gaussian, and some interaction V0, which can be a priori complicated. So the measure nu0, we're going to denote the expectation with respect to the measure nu0 here, and this expectation can be decomposed in the following way. It is a Gaussian expectation with respect to some covariance C infinite, because that will be this Gaussian expectation, and C infinite is just the inverse of A. And this Gaussian expectation is taken on exponential minus V0, the potential, and the function f we are interested in. So there's an extra normalization function as usual. So the strategy will be to do a blocking procedure and say that the Gaussian expectation here, since we have a covariance C infinity, we can split it into two parts. So let me insist on the notation. So C infinity is the inverse of A minus 1. There are many ways to rewrite E minus 1, but one way is just the integral of the exponential minus TA between 0 and infinity. And we will denote by CT the integral between 0 to t of exponential minus SA. So now the idea, which is so basically only the first part of this integral. So now the idea is to say, okay, we have a Gaussian field. Let's decompose it into the sum of two independent Gaussian fields, because we can split the covariance into two parts. So the Gaussian field X, which is here, will be decomposed into two fields, phi and zeta. And now the expectation is over phi and over zeta, because this part is the covariance of phi and the other part is the covariance of zeta. So we have this double, now we split the field into two parts, and we're going to integrate it part by part. So here is a summary of what I said, I guess. I'm just confused, I can't read what half of the screen disappeared, sorry, okay. Yes, so we're going to integrate first, we're going to integrate the, oops, sorry, excuse me. First, we're going to integrate the part which corresponds to zeta, which is the fast field. And then in the second step, we will integrate the field phi. Okay. So that's the idea of the decomposition, is really to think of zeta as the modes which were at level 1, the blue modes, and phi is already the renormalized part. It's one step above. So now the function, let me summarize. We have defined a notion of expectation in terms of the two Gaussian variables, and the idea is that the zeta part has covariance C of t, and it should basically describe the averaging of the field on blocks of size square root of t. By the way, t is space now and not time. And the example we can keep in mind is again our Sine-Gordon model, where A stands for the discrete Laplacian plus epsilon square, and V or V0 is Z times cos xi. So we have the field with okay, so time is running fast. So now we have the expectation which is written above, and we decide to integrate first with respect to zeta, then with respect to phi. So to make it a bit more complicated, I'm going to introduce now the notion of a renormalized potential, which is over there. It's a potential V of t, and the exponential of or V of t is defined in this way as some integral with respect to zeta for a given phi. So the idea is very much like we're going to freeze the phi and then integrate over zeta. In a sense, the renormalized measure at the level of phi will be now the Gaussian measure with respect to the covariance of phi and a new potential, which is no longer V0, but V of t. So this first part can be decomposed or rewritten as just the expectation with respect to a new measure, nu t, and in terms of a function which looks very complicated, and we simply going to say that this function depends on phi, and we want to interpret it as a semigroup. And this semigroup will be given by P0TF. It's a Polchinski semigroup. So let me briefly summarize. We started from a measure at scale 0, and we partially integrated it with respect to zeta, leading to now a function depending only on the phi, which is a slow field, and we integrate this function with respect to a new measure. So once integrated, we hope that the field phi is kind of better and smoother, and we hope we can control this semigroup. So that's our goal. We now have a way to rewrite any expectation on nu zero in terms of the expectation of a measure which should be smoother at level t. And we have a notion of semigroup. So the semigroup looks horrible as it is. However, it has a beautiful structure. And in particular, if you take the time derivative with respect to t or with respect to s, you obtain a time-dependent generator, L, curly L, which has a form very similar to the semigroup we saw earlier on, which is the Glauber semigroup. So it turns out that, of course, this semigroup is a bit more complicated because now it will depend on the covariance. So let's say in this notation, C dot is exponential minus TA, and the semigroup depends on C dot, the Laplacian as a weight depending on C dot. C dot is the covariance of the system or related to the covariance of the system. And in the same way, here the scalar product depends on C dot. But nevertheless, what we saw is that the semigroup has a structure which is reminiscent of the one of the Glauber dynamics. And the hope is that they'll be averaging on blocks due to this C dot, which changes with time. So let me try to conclude the very important point now. This semigroup depends on a potential V, and this potential follows some equation, and this equation is a Hamilton-Jacobi equation. So if we want to understand the semigroup, the Polchinski semigroup, we have to understand also the evolution of this renormalized potential along the Hamilton-Jacobi equation. Okay, that is potentially very complicated, and it will be extremely model dependent. So let me give you an idea of the type of theorem we proved with Roland, and that's the main point of this talk. Let's say we start with a Gibbs measure with the potential written, the potential here. Then assume two things. First, that okay, the A is not completely degenerate, but the lambda can be tiny. And assume that we have a good control on the Hessian of the renormalized potential. So good control in a sense that it's bounded from below by some factor mu dot. And we, of course, will require that this bound holds for all the, this control holds for any scale, for any t. Then we can derive from this bound, which is very much like a multi-scale Baikri-Emery bound, because it's a control of the Hessian of the potential, renormalized potential. We can deduce a log Sobolev inequality, which depend on all these parameters. So, of course, for this to be efficient, one has to prove that this criterion holds for the model we consider. But the interesting, of course, or the interesting feature of this criterion is that unlike the Bakri-Emery criterion, the mu dots can be negative. So there can be some negative part in the potential. The only important fact is that the renormalization group ensure that this negative part is going to become better and better, or more and more positive, or less and less negative along the renormalization flow. And from that, we can still get quantitative estimates. I will just go through the proof extremely quickly, and if possible, because I think it's important for Roland, if he wants to give his talk, that I covered enough material. I'm very sorry, Roland. You may. So just give you the idea. So there can be other criteria than the one we presented here. There are many ways to quantify this lower bound on deviation, but they all of the same nature, that if deviation is under control, then one can deduce a log Sobolev inequality. And the proof will be shorter because it's very much in the spirit of Bakri-Emery proof I explained before. We want to understand the difference between two terms, this one and this one. And so we choose a semigroup. Now it's a Polchinski semigroup. We view this as a difference between the semigroup taken at different time, and we proceed as in Bakri-Emery proofs. And it turns out that
sorry, the top is not visible again.
Sorry,
the top is
yep. Okay, I hope it's better. Whoops. And the semigroup has the same, or what happens is that we can use the same structure as standard Glauber semigroup and proof or reduce to estimates which are very similar, like the one I've showed here. And in particular, sorry, this quantity, which is here, has the same flavor as in the Bakri-Emery proof, with the exception that now the measure is evolving with time, and the time acts as a special renormalization, and the semigroup evolves also with the time t. So let me now just conclude. Once we have this structure, one can actually prove with our convexity assumption an estimate as in Bakri-Emery proof, which allows to control the gradient of the square root of PTF and complete the proof of the log Sobolev inequality. So there, our new estimate, our new convexity assumption allows us to close the equation and proceed as in Bakri-Emery. And now the whole question is trying to get some quantitative results, because what I've shown you is a very abstract criterion to prove log Sobolev estimates if one understands well the effective potential along the renormalization flow. And now what Roland will explain next is can we make this quantitative on more specific models, and how can we implement this. Sorry, I've been too long, excuse me.
Very good. Okay, so let's thank Thierry for his talk. And now, just maybe a quick question, so we will go ahead with the schedule. There have been already a few questions during the talk, so.
Yeah, but I'm sure with Roland's talk, everything will become clearer because you'll see
Okay.
the example.
So in that case, okay, let's thank Thierry again and prepare for Roland's talk.
Thank you.
So Roland, we cannot hear you.
How about now? Hello? How about now?
Not much, Roland. I think,
You can barely hear.
yeah.
And now you're just muted.
How about now?
Perfect.
It's better. It could be a little louder, but it's better.
Could be louder. Okay, let me see. So somehow Zoom on Linux is always a hassle. So is this better now?
Yeah, that's fine. That's fine.
Okay. So someone needs to give my iPad permission to share my screen. So I can't do that right now, I think. Oh, no, now it works. Okay. Thank you. So let me know when you'd like me to start. Is there a break now, or am I supposed to start right away?
So Amanda, you're chairing, right? So you can decide.
Maybe should we have a 2-minute break and start at 3:10, just to give people a little bit of time just to get a cup of coffee or something?
Sure.
Okay, so welcome back to the second talk of today's One World Property seminar. So we've got Roland Bauerschmidt from Cambridge, who's going to talk about spectral gap for strongly correlated spin models.
Okay, well, thank you very much for the invitation to speak here. My second part of this talk will provide some complementary details on what Thierry already explained. And let me briefly recap the setting we're interested in. So we're looking at probability measures, which will usually be denoted by nu on R to the lambda, and lambda is a finite set which we usually like to think as a subset of ZD. But for much of what Thierry explained in the second half of his talk, the precise structure didn't matter very much. But we'd like to think of lambda as a subset of ZD. And so spins are continuous or real valued at every site of this lattice. But again, this is I will fix this convention mostly throughout, but it's not essential. In fact, we could also look at vector valued spins, or also this setting also even fits discrete spins, and I'll mention some examples later on. But I want to introduce an additional distinction that wasn't present in Thierry's talk, which is that between a lattice problem and a continuum problem. So in physics terminology, these two different regimes of scaling that I will discuss would be called the infrared problem or the ultraviolet problem. And this can be an incredibly confusing point. But I want to spend a little bit of explanation on this because it helps to place the different models that will appear into better context, and also to relate. Okay, so we'll get there. So what this means, in other words, is we'll think of lambda either as a subset of the unit lattice, or we think of lambda as a subset of lattice of mesh size epsilon. Of course, you can always rescale the epsilon lattice back to unit lattice. The reason I want to keep these two lattices is that along with the different choice of lattice, we usually have a different choice of parameters in our Hamiltonian H. And that will be related to this lattice spacing epsilon. And okay, so once we have such a subset, as always, we're interested in taking a large subset. If we're considering the unit lattice problem, well, then we'll need to take basically this parameter L, which is the length of the domain, to infinity to have an infinite number of points. But if we consider the continuum problem, where we have a mesh size of length epsilon, you can even study infinitely many points with L fixed. So you take a macroscopically finite size of a domain and epsilon to 0, that will also take the number of points to infinity. And of course, then you can also do both. You could take epsilon to 0 and L to infinity. And so the class of measures are of the form H of phi, consists of the first part, which is like this nearest neighbor interaction that Thierry presented, and a local potential. So local meaning it's summed over all points, but it's the case we're interested in, it's non-convex. And so here I've inserted the epsilons, how they appear naturally, and that gives you some idea of how of why I wrote why I'm distinguishing the epsilon lattice. The first term, you need to scale the epsilons so that basically the difference of phi's looks like a second derivative, and then the sum becomes an integral. And you don't do that for the potential term. Okay, so however, it turns out that if you're looking at the continuum scaling, you will need to take. So I just told you that you don't put another 1 over epsilon term into the potential term. Now I have to correct what I just said, because if you follow this procedure and try to take epsilon to 0, the only limiting measures you will see are trivial or Gaussian measures. So in practice, in this continuum regime, you will also look at potentials that depend on epsilon. And this will become clear in the concrete examples later on. I just want to emphasize the setting. There are two different scaling regimes. One is the large distance, the large scaling on a unit lattice, say. The other one is, say, fixed size domain and the small distance scaling. And they have slightly different physical motivation and physical features. So the basic models that already appeared in Thierry's talk we have in mind are, say, a double well potential. So if you're on a unit lattice, this double well potential is, say, of the form phi to the 4 minus phi squared. In general, we allow some coupling constants in front of the phi 4 and phi squared term. The constant terms in front of the phi squared term is usually negative, so that we have a double well. The other case is the periodic potential, or in this case, the lattice sine Gordon model, where the interaction would be like say periodic potential, let's say cosine. And again, one can modulate, one can put in parameters, and the most important parameter is the periodicity of this potential, which we'll see has an effect on how these models behave. So these are the models at a unit lattice scale. So somehow this is the problem. These are the models, maybe if you're coming from statistical mechanics that you'd be interested in. But often it's, but there's another, as I mentioned, there's also the epsilon to 0 limits which are of interest. So here we're looking at the lattice of mesh size epsilon. We can define the same models. But now our goal is to choose these potentials in such a way that if you take epsilon to 0, you get a non-Gaussian measure. So somehow you keep enough, you keep the interesting behavior of the potential. And as I just said, you cannot do that by keeping the parameters fixed. So you need to make the parameters depending on epsilon. And so these are the infamous counter terms of quantum field theory, and more recently popular in the study of SPDEs. So in this regime, you have to choose these epsilon dependent constants, and then it turns out if you do this in the correct way, you can take epsilon to 0, and these limits converge to non-Gaussian measures, say on Schwartz distributions. Okay, so these are the general class of models we have in mind. And to understand what's going on, it's essential to understand very well what's happening in the, in quotation marks, trivial case, where we don't have any interaction whatsoever. And that's just the Gaussian free field, in which case there's no potential. All of the interaction is coming through this quadratic Gaussian term. Of course, as many of you know very well, the Gaussian free field is one of the reasons it's interesting is that it fluctuates on all scales. So it's a Gaussian field, so it's completely encoded by its covariance. And its covariance is the Green's function of the Laplacian, or simple random walk if you prefer. And so in 2 dimensions, this behaves logarithmic. So there's strong correlations. And in higher dimensions, there's still strong polynomial correlations. The Gaussian free field is at least in the limit epsilon to 0 exactly scale invariant. So in some sense, the problem of understanding small scales is the same as the problem of understanding large scales. This is something that once we add a non-convex interaction, is not the case anymore, and the reason why I've been emphasizing so much that there are these 2 regimes that are really different. The small scales and the large scales are not the same problems. Okay, so anyway, so this is the free field, which is sort of the basis for everything. So I will explain some of the things that we can understand in exactly the setting I just presented. But we cannot understand all of the models I presented to you in this setting. And there is, so I'll introduce also a little cheat, in which case, assuming which we can do much more. We'd like to get rid of this for those cases, but let me mention this. This is what is called, goes under different names. I like to call it the hierarchical Gaussian free field. It's also known as the branching random walk. Related to this, it's basically a cheat which captures the essential structure of the free field while simplifying its effective geometry in a considerable way. So what is it? So here I've drawn a picture in 2 dimensions because it's easier to draw, but you can do this in any dimension. So in 2 dimensions, we start with, say, a square. We divide it into nested subsquares. Keep doing this. And then we define a field, Gaussian field, which I'm again going to call phi, by at a point x on this cube. So think of this cube as, say, ZD, a cube in ZD, a large cube in ZD. So at any point, we define the field by summing over all cubes that contain this point x that we're looking at. So we have a point x. We're summing over all boxes that contain x. And then what are we summing? Well, we're summing basically independent Gaussian, say, standard Gaussian variables, which I'll call phi tilde of x. So one for each cube. They're independent over all cubes, but the same, well, for the same cube, obviously. And then there's a, oops, that was the wrong, and then there's a scaling factor that you can put here. And if you do this construction, you can convince yourself that the covariance of this field behaves in a similar way to that of the Gaussian free field. It behaves logarithmic in the distance and 2-dimensional. It behaves polynomial with the exponent, with the same exponent in higher dimensions. Now here I haven't told you what these approximate means, and this is where the difference lies. If I had written equal, this would be the free field, but it's not equal. So here approximate is something that is maybe upper and lower bounds, okay, but it's not asymptotic, for example. Once you reach the boundaries of these boxes, this field behaves differently from the free field. Nonetheless, it captures a lot of the structure of the free field, and in this business of understanding renormalization, it's been you know, an important stepping stone to understanding more complicated models. Now, I wish I could tell you that once you understand the hierarchical field, we also understand the general free field. Unfortunately, that's not the case. At least not for the problems we're considering. We don't know how to use the hierarchical results and transfer them to the real free field. But basically, they serve sort of as a stepping stone for us. But there are in fact examples, say, for example, in the study of maxima of Gaussian fields by Bramson, Zaitouni, Ding, etc., where such hierarchical fields really could be used to provide the key ingredient for the real models. So anyway, so for me, they will be you know, I will explain them as something, as a convincing evidence of what we think is true, and also in the general case, but not all of the results we can do in the real case. Maybe let me quickly mention that another way to think of this hierarchical field is that this phi, this formula I wrote for this field phi is basically a Fourier decomposition. In fact, you can really think of it. It's a Fourier decomposition with respect to a certain hierarchical group. You should compare it with the Fourier decomposition on of the free field on ZD. And you can, if you do this identification, you can see there's a lot of similarities. The scaling factor has basically the interpretation of the 1/k squared and the Fourier decomposition of the free field, and so on. But okay, so I see there's a question in the chat. Why not consider it on a flat torus to get rid of boundary effects? There's no boundary here, really. There are no boundary effects, really. I mean, there's boundary effects on the, I mean, there are these nested boxes, and there's boundary effects there. But okay, so maybe we can talk about this towards the end, but I already spent a bit more time on this than I was hoping I would. Okay, so okay, so this is these are the models we have in mind. We have these, so let me quickly, since I spent so much time there, we basically have these types of models in mind, different regimes one can consider, and for some of these, I will allow the cheat to replace the free field by the hierarchical one. Okay. So as Thierry explained, so these models are all of the form. There's a measure which has a form which is, there's formally a quadratic term like this, and then there's a potential term minus v. And as Thierry explained, we've devised this general strategy to prove to obtain dynamical information for these types of models in the form of a Log-Sobolev inequality by studying, instead of this potential that appears in this definition, this renormalized potential, which I will quickly recall was defined as follows. We identify that the Gaussian part of the measure has a nice structure, in the sense it's inverse, which is the covariance of the Gaussian measure. Admits a scale decomposition. So here I wrote the heat kernel decomposition, which we're using in the continuum, and in the hierarchical case, there's a similar decomposition that makes more use of this explicit hierarchical structure. And this will allow us to decompose the Gaussian measure, as Thierry explained, and ultimately define this so-called renormalized potential, which in some sense captures the structure of the model at length scales related to this parameter S, which we can vary. And as Thierry explained, understanding this whole scale of potentials is incredibly useful, because it allows us to obtain dynamical information, which we cannot do by just studying a single scale, because the dynamics is really, because on a single scale, there's no notion of convexity that is useful in this context. While having all scales available, it suffices to control the Hessian at every scale S. So we control the Hessian of the renormalized potential at every scale S in terms of some constant mu dot, which can be negative, as Thierry explained. This formula looks a little bit, okay, so the Hessian is sandwiched on both sides by this e to the minus SA over 2, which is the heat kernel associated to this Laplacian A. So this might look a little bit scary at first, but I suggest you ignore this for now, and trust me that having these two terms on the sides is strictly helpful. It just generates more smoothing. So the upshot of all of this recap, which took me longer than I thought, is that we need to control these renormalized potentials. Okay, so in the remainder of the talk, I'd like to explain some of the examples where we can do this. I will start with the hierarchical models and the large scale regime, and then I will talk about models which are not hierarchical, but in the continuum. So this corresponds to an SPDE, where we can do it in the real case, because somehow the SPDE scaling is much simpler to control than the lattice scaling. Okay, so let me say a bit more concretely. So we start with the critical phi-4 model. As Thierry explained, this is kind of like a continuous Ising model. So the measure has like 3 terms in the potential. The first one is the interaction term, which I'm taking to be the hierarchical Laplacian here. Then there's this phi-4 potential, so it's g phi to the 4 and nu phi squared. Choosing g positive, as we'll always do, and nu negative, which we'll also always do. This is a double well, and you can see that the width of the 2 wells is basically controlled by the parameters. So if you take nu very negative, the 2 wells are far apart. If you take nu just a little bit negative, they're close together. And we think of varying nu as a temperature. In fact, Thierry wrote this a little bit differently in the beginning, but you can translate to this setting. So okay, so varying nu corresponds to varying the temperature. And so we'd like to understand what happens if you vary nu. Now, what happens is as is well known, there's a phase transition in this model. If you take nu very negative, there is long-range order. Roughly speaking, this means that typically the field phi is trapped in one of the wells. So that is for nu less than nu c. So remember, nu c is negative, so the wells are far apart. In this case, the field is somehow trapped in one of the wells, and as a consequence, taking the sum over phi x, phi 0 will not decay, and it's not summable. On the other hand, if you take the wells close enough together, but the potential is still non-convex, but close enough together, in this case, the effect of the wells somehow washes out, and the model behaves effectively as if you had a convex potential. And as a consequence, the sum over this two-point function is summable. So this is the phase transition of this model. And okay, so this is the static picture, right? So this is the static phase transition of this 5-4 model. This is basically, you should think of this is completely analogous to the phase transition that you may be more familiar with of an Ising model, where you vary the temperature. At high temperature, there's fast decay of correlations. At low temperature, there's long range order. This is exactly the same, except it's the continuous spin version of this. The problem we're interested in is what happens dynamically. So this description of the phase transition, as I presented, is a static picture. We know in equilibrium how these configurations behave. What we'd like to understand is, if you run, say, this continuous Glauber dynamics as introduced by Thierry, how does, what happens near the phase transition in terms of the dynamics of the model? This is as Thierry explained, while we understand very well a lot of the static feature of these type models, much less is known about the dynamics. The usual tools that are effective in terms of for the study of the static models become usually ineffective. Monotonicity is much harder to get, etc. The basic question that we are interested in, it's not the only one that's of interest, but the one basic question we've been trying to understand a bit is, what about this critical slowdown? So there's, as you approach the critical temperature from above, so for nu strictly bigger than nu c, we know there's, for nu large enough, we know there's fast dynamical relaxation. For nu bigger than nu c, we know there's fast static decorrelation in some sense, weak sense. What we'd like to know is how the dynamics become slow as we approach the critical temperature. So this is goes under the name of critical slowdown. And in this, so this is a problem that we can only study in this hierarchical setting so far. But in this case, we can get a relatively satisfying result. So this is, I will maybe say a few things about this in a second. So this is, we're looking at the 4-dimensional case for certain reasons that maybe I'll explain in a little bit, but let me explain it now while I'm discussing it anyway. In some sense, in 3 dimensions, no one knows what's going on with these models. It becomes much harder. The picture is, the higher the dimension, sort of the more manageable the effect of the nonlinearities becomes. 4 dimensions is the marginal dimension, where sort of things happen that are very that are different from the mean field scaling, but it's still somewhat manageable. And so that's why we're considering the 4-dimensional case here. So now I can see there's, how do you deal with the lack of the explicit knowledge of the critical temperature? Okay, so that's a good question. Well, I will maybe answer it in a minute after presenting the result, when I'll give you a brief indication of how the understanding of this case works. And I'll explain this in a second. So let me first say, okay, so what can we do? So we're looking at this 5-4 model with a small interaction potential. In this case, we can say that the Log-Sobolev constant slightly above the critical temperature, so we're going to the critical temperature plus delta, is bounded above and below roughly by delta. But then there is a logarithmic correction, which in fact shows us that the gap is strictly smaller than that of the free field. So So we can get these upper and lower bounds, which are of order delta. This is what you'd have if you have a free field with a, like, say, a mass term of order delta added to it. But in this case, because of the nonlinearity of the interaction, we have a strictly faster closing of the gap as the critical temperature is approached. So there, as I mentioned, there's two. So this is two bounds. This is an upper and a lower bound on the spectral gap. They essentially match, but not quite. There's an upper bound. So basically the powers of the logarithms don't match. So if to some extent you might say, okay, that's fine. You're not interested in the exact power of the logarithm. There's a little bit of interest in this power of the logarithm because this goes a little bit beyond of what I'll be able to explain today, but it's sort of the power of the logarithm captures sort of in this renormalization group picture the bifurcation of the fixed points that is happening in 4 dimensions. So understanding these powers of the logarithm is of some interest, but maybe it's not something that I will explain at this point because I would go a little bit too far. But let me quickly comment on the two upper and lower bounds because they are of very different nature. To get an upper bound on the spectral gap, you just need to put in the right test function, right? The spectral gap has a variational characterization. If you plug in any test function, you get an upper bound on the spectral gap. So to get this upper bound, you just need to plug in the right test function. This test function is what is called the susceptibility. You can plug that in. And of course, computing the susceptibility isn't an easy task. But in this setting, we know very well how this behaves. In fact, they're in good at least upper and lower bounds in, well, maybe they're not good in all dimensions, but there are non-trivial upper and lower bounds in all dimensions, actually. So, so in our case, we know precise. In fact, we can get this precise upper bound also in the non-hierarchical case on ZD. This is something that that was sort of the point of motivation for us. This is a static question that we understand very well. So the dynamically non-trivial bound is the lower bound on the gap. So that's the other bound. Oops. So that's the blue one. And so to get this lower bound, so that the lower bound on the spectral gap, so that gives you the rate of, it tells you that the relaxation is at least as fast as given by this bound. For this, we use this criterion based on the Polchinski equation that Thierry explained and that I recapped. So this uses and so if you recall, this uses the structure of these renormalized potentials at all scales. And I'm not going to have time to explain in detail what that looks like, but I want to show the picture. And I think that also allows me to, at least at the level of the picture, answer the question, one of the questions that appeared in Thierry's part, and also a question that Milton asked. So our initial potential, which I called denoted here by V0, is a double well. Now, it turns out that once you do these renormalization group steps, the right way to think of the effective potential is that it's again a double well, but the shape of the double well changes a little bit. So this picture is a little bit too simplified if you're on the real ZD model, because the actual potential is not a function of a single variable. It's a lot more complicated, unfortunately. But in the hierarchical case, this picture is actually pretty close to the truth. And so really what happens is you start with a double well, and we can track quite precisely how this double well changes from one scale to the next. And in the regime we're looking at, it becomes it becomes flatter and flatter. And what happens is, as long as you're above the critical temperature, it will eventually become convex. How long that takes is related to how big the gap is. If you're exactly at the critical temperature, it will never become convex, but sort of you obtain asymptotically the effective mean field picture where, you know, the second derivative eventually becomes 0 and it looks like x to the 4th or something like this. Now, how do we deal with the fact that we don't know the critical temperature exactly? Well, the critical temperature is defined implicitly as sort of the maximal temperature such that, the maximal nu, such that under this iteration, the effective potential just doesn't become convex anymore. That's the critical temperature defined in the renormalization group picture. And and this is how it's characterized. So it goes along with, you know, okay. And okay, so this is the picture, and you know, from this picture you can compute the Hessians of these renormalized potentials. You can plug it into this formula that Thierry showed, or Thierry essentially proved, and that I recalled. And from this, you can you know, get an estimate on the Log-Sobolev constant, and it's you have to do this relatively precisely to get these logarithms correctly. Well, we don't get them correctly. The logarithm on the lower bound doesn't match the upper bound. But you have to do this relatively precisely to get the logarithms at all. But okay, so this is what I wanted to say about the phi-4 model, and I'll be discussing a few other models now. Let me mention that, okay, it's would be we'd love to be able to do this in the non-hierarchical model, but it's a hard problem, I think. I'll tell you about non-hierarchical models a little bit later. Let me quickly mention another model that Thierry already mentioned, which is the hierarchical lattice sign-Gordon model. So this is similarly defined to this phi-4 model, with the difference that the potential is now periodic rather than a double well. So it looks like this. Again, we're looking at this hierarchical version of it. So it's basically this hierarchical free field modulated by a periodic potential. Written like this, if you're paying close attention, you'll notice that there's a little bit of an issue because, this potential V is invariant under shifting everything by a constant, or constant divided by square root beta. So you cannot define the measure of this. It's not normalizable, in other words. So you have to do something, and there's various things you could do. A natural thing would be, for example, to fix the spins at a single point. It wouldn't really be a problem, but we just picked the most convenient because it's basically we picked the most convenient thing you can do here, which are all morally equivalent, which is to basically add a small quadratic term, which has a tiny prefactor, L to the minus 2n. So this is 1 over the volume times, and then there's another volume here. So this is really tiny quadratic term, which basically just stabilizes the potential. And roughly speaking, this amounts to fixing the spin at a single point, but doing this uniformly over all points. It's slightly more convenient to work with, but there's no essential difference. So this is just to explain that we've added a little extra term here. Well, then you can do a back of the envelope calculation. So this is sort of the type of calculation that corresponds to the picture for the effective potential of the phi-4 model that I explained. And this will tell you that, well, if you close your eyes and work to first order and pretend that this effective potential is always a cosine, there's a scaling computation you can do, which is that this coupling constant in front of the coastline changes from one scale to the next in a way that depends on L, which is a positive constant bigger than 1, and some scaling factor that depends on this temperature beta and on the dimension 2. So this is something that has to do with, I mean, that it comes out in this way is basically has to do with the logarithmic correlations of this two-dimensional free field. But okay, so this is a back of the envelope calculation. It's not hard to do. I mean, harder to do is to justify it But so this is the basic heuristic. And you can see from this that there's a difference whether beta times this constant sigma is bigger than 2 or less than 2. If it's bigger than 2, this prefactor that I've highlighted here is going down exponentially. If it's less than 2, it grows exponentially. And again, this determines that there's a phase transition in this model. If beta is sufficiently large over a critical value, then the effect of this cosine interaction diminishes for bigger and bigger scales. In fact, the scaling limit of this model is a free field. Or in other words, one way to measure it would be to say the field is rough. The variance of the field at a single point is, say, logarithmic in n. On the other hand, if beta is less than the critical value, what would be expected is that, at least if it's far less than the critical value is known, at least in the nearest neighbor lattice, that then the variance of the field is on the other hand bounded. So if you're in the nearest neighbor lattice, this would be like a Piles argument that the field is localized. So there's this transition between localized and rough, and the case we're interested in is mostly the rough phase, where the field looks like has strong. So the rough phase looks like a free field. It's not a free field, but it sort of has the correlation, the fluctuations of a free field, and we'd like to be able to say anything dynamically in this setting where there's these strong correlations that form. And in this case, what we can say under certain assumptions, coupling constant is small, we're above this critical value, is that the gap or the Log-Sobolev constant behaves like that of a free field on the size of the box. So it's like L to the minus 2n on a box of size of diameter L to the n. Again, this result, as I presented here, is only in the hierarchical case. We cannot do this in the non-hierarchical case. Let me mention another result that's closely related to this Sine-Gordon model, which goes under the name discrete Gaussian model or integer valued Gaussian model or Z ferromagnet or other names, which is just a free field conditioned to be integer valued. This basically corresponds to, you can again do this in this hierarchical setting, you condition it to be integer valued. So integer valued of a certain variance, and now the variance, again, you can vary the variance and there's a phase transition. This is pretty much physically the same as in the Sine-Gordon model. The integer valued constraint is just a hard version of this periodic potential, right? It's again, periodic constraint is just a hard version of it rather than a soft one. So it's like Ising model compared to phi-4. And I'm just mentioning this result to demonstrate that these methods we've been trying to develop are not really restricted to the continuous spins, but in this case, for example, it's not very difficult to consider the hard interaction as well. And we see the gap is again at beta sufficiently large, or should this be small? Anyway, there's some confusion about beta, 1 over beta, but this is the rough phase where it behaves like a free field. Okay, anyway, so finally, I'd like to explain some progress on results which are not using this simplification of the hierarchical lattice, but instead work on the real continuum setting. In this case, we're looking at the Sine-Gordon model with in the continuum normalization. So as I explained, so here we're thinking of a lattice of mesh size epsilon. There is the interaction is tuned in such a way by this term, so that as epsilon goes to 0, you obtain a non-Gaussian measure, which is supported on Schwartz distributions, say. So at least if the parameters are chosen in the right way, which means I'm not going to explain in detail what the precise assumptions and conditions are to get this, but let me emphasize that there are some conditions you need to enforce here, which let's say in the SPDE language would be to ensure that the model is subcritical, or in the quantum field theory terminology, that it's super renormalizable. But if you do this in the correct way, you can tune these parameters in such a way that as epsilon goes to 0, you obtain a non-Gaussian measure supported on Schwartz distributions. In this case, say Schwartz distributions, or say of a torus of side length L. So the Glauber dynamics that Thierry explained is then singular SPDE, which is of the type studied by Hao Shen and Martin Hira and Ajay Chandra. So they've studied this equation in particular. So it's one of the singular SPDEs. We're looking at it as a sort of as a weakly interacting particle system, which is sort of dual or alternative point of view, but it's physically the same as the SPDE. So in this case, we can prove the Log-Sobolev inequality for this model, basically assuming that this parameter beta is less than, okay, I'm not going to go into this because I don't want to bore everyone who's not familiar with the details of the models, but let me just say there is a non-technical assumption which or half technical assumption, under which cases we can get the Log-Sobolev constant independently of epsilon. So in other words, it passes to the continuum limit. So this is in any finite volume. And then in this case, we and for all positive coupling constant, not necessarily small, but if the coupling constants are small, we can also pass to the infinite volume limit. Or in other words, we have an estimate which is quantitative and uniformly in the volume. So basically, to sum up, we understand this model as well as we could hope in terms of the Log-Sobolev inequality. It would be very natural to look at the corresponding double well model. So this is this continuum phi-4 model. So I'm not going to go into the details of this definition, but let me again mention that this would fall very naturally in our framework. One can define this renormalized potential. In the hierarchical model, this would be much easier for us to analyze than the long distance problem we looked at, which has a much stronger scaling than the continuum limit. But in the continuum, we haven't succeeded in treating this model, though there is quite convincing evidence that it should be. So the Log-Sobolev inequality is open, but using different methods, the spectral gap has been established, in particular in this work by Henrik Weber and Pavlos Tsapsulis, who are using SPDE techniques. And I think it would be very interesting to get the Log-Sobolev inequality in this case as well. Okay, so finally, okay, so let me give you a brief idea. So in the hierarchical case, I gave you a few pictures of how the effective potential evolves. Let me say briefly in this case what we can do in this case. So we in this case there's a beautiful way of understanding this effective potential, which is based on a duality with a Coulomb gas. So basically, we can seek periodic solutions of the effective potential. So we write sort of a Fourier ansatz for this. Let me not go into the details of this because it looks a little bit complicated, but basically, let me say that, or let me emphasize is that this is sort of a not standard Fourier representation in which you can think of all the terms of Fourier coefficients as sort of partition functions of a certain Coulomb gas with plus and minus charges. So this is, and then as was observed by Bridges and Kennedy, one can get a very effective control of understanding this effective potential by, you can now solve the Polchinski equation by basically using the Duhamel formula to obtain integral representation for these Fourier coefficients, which you can sort of estimate inductively. Okay, so in the remaining few minutes, let me quickly, or let me mention a final example, which doesn't really fall into the class of examples that I've explained too much, but it's much simpler, and it exemplifies a certain point of our approach, which is that it's not only useful if, our emphasis has been on, obtaining a different, more or structurally more efficient way compared to the usually used spatial decoupling and these type of models, which is based on, this renormalization procedure, which is less spatial, but sort of half spatial and half, in the height of the field, which has, for us, certain important technical, which we think is, okay, which in the examples we've seen is, can be controlled in the regime where there are strong correlations, which we somehow couldn't hope with in the spatial approach. But there's an example I'd like to mention because it's very simple, is a mean field example, but disordered, which is the Sheraton-Kirkpatrick model. So this is so here the spins are on the hypercube plus minus 1 to the n. So the sigma. So this is also discrete. And then there's a coupling matrix, which is so this, like this. The spin coupling matrix is just a Gaussian orthogonal ensemble matrix, which is another way of saying that it's just a matrix, symmetric matrix with all entries IID Gaussian. Now, if you try to apply, and it comes with a temperature parameter beta. Now you can try to apply the usual methods that are usually effective at high temperature to obtain information on the dynamics of this model, say prove the Loxobolev inequality or spectral gap. But you'll see quickly that the usual methods fail by a huge factor, because they usually require some condition on the couplings. So basically you need to have these spin couplings which appear in the interaction, and usually they need to be summable, and if after multiplying by this parameter beta, they need to be small. Now in this case, for the GOE, if you take the sum of the absolute value of the spin couplings, this is of order square root n. It diverges in a very bad way. These estimates would be so these are the usual estimates that go back to maybe Zygalinsky and Struck and many sort of implicit in many other works. Using this kind of approach that's based on this Polchinski flow, we don't write it exactly in this form. We write it much more explicitly in this example. But here we can see that rather than needing to control this sum of the absolute values of the GOE matrix, it suffices to have a spectral estimate on this GOE matrix. So in other words, it suffices to control the operator norm, which by standard random matrix estimates is bounded by a constant. So it's bounded by a constant rather than by square root n. So it behaves vastly different. And so sort of our method allows to, very simple in this case, the whole proof is only a page, get the Loxobolev inequality for this SK model for temperatures that are sufficiently high. High beta less than 1/4. This doesn't go up to the critical temperature, but sort of it gives a uniform bound in this regime. And in fact, there's been a nice recent work that so here we're talking discrete. So I would have to tell you what the Dirichlet form is, and there's a certain flexibility of the Dirichlet form, since these spin couplings are not bounded, so there's different Dirichlet forms are inequivalent, and there's been a recent work on a different Dirichlet form and a different approach to this as well. But anyway, I think it's it's an example that illustrates some of the features which I haven't been emphasized so much in the rest of my talk, which is of this approach to the Log-Sobolev inequality. And I think my time is pretty much up at this point, and luckily I've said everything I wanted to say, and thank you for your attention.
Okay, so if you'd like to unmute yourself, we can all thank Roland. So do we have any questions? Either you can write them in the chat or raise your hand. Yeah, so there's a question in the chat. Just a second.
Okay,
from Gabor.
Yeah. Is it known? Okay, so Gabor's question, maybe let me rephrase it. So he's asking that, so I explained how the critical temperature is characterized in terms of this flow of effective potentials. Now, while you can always define this flow of this effective potentials, there's only few cases where we could really control it and, you know, use this to narrow down what the critical value is. And if it does, you can, you know, show that it satisfies the same. So, for example, that it's the unique point that where the susceptibility would diverge. So it corresponds with other definitions you would give. In general, the question I cannot answer, because in general we don't know how to control this effective potential. It's we'd love to, but in general this is hard. So okay, I don't know if that answers your question. Is uniqueness at nu C known? So again, in this case, let me see. So we're talking about ZD or on ZD, not the hierarchical case, but the ZD case. So let me, oh, my iPad just turned off anyway. Let me, I mean, this should follow, I mean, you should be, I mean, so this method is not made, so somehow with this method, we would be studying, for example, the limit you obtain through a sequence of torus approximations. I suppose if you talk about uniqueness, you would like to ask for the variation in the boundary conditions. This is an interesting topic, but it's typically not easy to access this with this method, which is sort of even in the simplest translation invariant setting of a torus, it's hard to get the effective control of this renormalized potential. Okay, I'm not sure if this answers your question, but okay.
Are there other questions? Stephen, I don't know whether you wanted to come back with a question about your hierarchical field.
Yeah, actually, I had a slightly different question. It's maybe an orthogonal direction. So the Glauber dynamics is the non-conserved dynamics. Has anyone spent time and energy looking at the conservative versions, so-called Kawasaki dynamics?
Yes, so very good question. So in fact, for us, it doesn't. So we can look at the Kawasaki dynamics. Let me just make sure what I'm saying is correct. So certainly in this continuum case, in the Sine-Gordon case, we also looked at the Kawasaki case, and in fact, it doesn't make much of a difference for us. So to experts, this on a Kawasaki dynamics, this is usually a little bit surprising because it's usually infinitely harder to study the conservative dynamics than it is to study the Glauber dynamics. Somehow the difference is we need to control the effective potential anyway, which is sort of, and once you have that, the difference between the Kawasaki and the Glauber dynamics is, I mean, in terms of difficulty is not big. There's not much difference.
In a second, another orthogonal direction. What's known about quenching below the critical point? And I don't mean the phase, I mean the non-equilibrium dynamic side. If you quench below the critical point, you have essentially domain ordering dynamics. What's known?
Well, this would be a question that Thierry is much better at, would be much more qualified to answer. It's not what we've tried to understand here.
It's quite different, I see.
Yes, sorry, maybe if I can say, no, I mean, there's not much quantitative things which are known for unbounded system. There's more on Ising model on spectral gap, but it's becoming very sensitive to boundary condition, and okay, and our method don't apply in this regime at all.
Mm-hmm. Yeah, I mean, the reason for asking is I'm also interested in when you break the variational structure, but of course that's in some sense, also a question which you could ask in the critical case. What happens when you don't have strictly variational structure?
Okay, I don't think we can say much.
Yeah, it's very interesting talks. Thanks so much.
Okay, are there any last questions anyone would like to ask?
Okay, I would like to ask. Okay, just one more question. I had a list here, but maybe it's a little bit too much. But so I understand that looking at this Poshinsky equation to define the normalized potential is convenient because of the nice formulas that it provides. But is there any sort of reason to believe that is the best possible choice to do this?
It's hard to argue it would be, in the examples that we can, so you mean the best possible choice to do what?
Let's say you want to prove log Sobolev inequality or spectral gap inequality. In principle, you could have split your covariance in a different way, and maybe get different answer, no?
Yeah. So splitting the covariance in a different way, I think, is a technique. So we use we find, say, in the continuum case, we find the heat kernel decomposition particularly good technically, but I don't think this is you could imagine something that is morally the same and you should obtain the same results. But I think maybe this is not exactly what you meant, right? Okay, it's hard to argue that this is the best way of doing things, but I think we think that decomposing scale by scale in a way that doesn't maybe one way to say it is this is the way the physicists understand how you understand the effective scales of the model, and they usually have thought pretty hard about what the best way of things are. They're usually also very hard to make sense of or make rigorous, but in this case, I would say it seems to me that this is a very natural way of decomposing the scales. And of course, you might find different ways, but in the examples that we could treat, we found that we basically got optimal results somehow. We didn't really lose anything. So it seems, encouraging or supporting this. Okay, anything that works seems good, but yeah.
Okay, thank you.
So I have a question. May I ask?
Yes.
Okay. So for the last model, the dynamics with the Sherrington-Kirkpatrick model. So the log Sobolev inequality depends on the disorder, on the coupling constants.
Well, it's so with probability going to 1. Yes, so okay. It's quenched.
Okay. quench, so with probability going to 1 in the disorder.
Yes, so you fix exactly. So you fix so you on an event with probability going to 1 in the disorder, you have the Log-Sobolev inequality for the quenched measure.
Mm-hmm. But can you estimate have you quantitative bounds on this on the bad event?
I mean, the bad event is just that the largest eigenvalue is bigger than 2 plus epsilon. So these are just, so basically this is just large deviations of the largest eigenvalue for a Gaussian orthogonal, matrix. So this is things that are very well studied. I mean, so the bad, it's just basically what we added is completely deterministic. We replaced this usual assumption by one that only uses the extreme eigenvalues in that case, and then you can apply the random matrix results.
Okay, thanks.
Okay, if there are no further questions, I think we can all unmute ourselves and give both speakers another round of applause. And then I think that's pretty much it until next semester. So Alessandra and I will be in touch when we have the schedule for January. But in the meantime, I hope everyone has a very enjoyable Christmas, and let's hope 2021 is a slightly less bizarre year than 2020.